tutorial over 2.7 parent functions and transformations. Your new vocabulary is family of graphs, parent graph, parent function, constant function, identity function, quadratic function, translation, reflection, line of reflection, and dilation. A family of graphs is a group of graphs that display one or more similar characteristics. The parent graph, which is the graph of the parent function, is the simplest of the graphs in a family, meaning the parent function is the absolute most basic function in that family. Constant function, identity function, and quadratic function are going to be on the next slide. A translation moves the figure up, down, left, or right, and it's also known as a slide. A reflection flips a figure over a line called the line of reflection. So really the definition of reflection and line of reflection go together. And a dilation shrinks or enlarges a figure proportionally. We're moving on to the next slide to discuss constant, identity, and quadratic function. Okay, so what you want to do is anytime you see a flat line on your picture, you're automatically going to think it's the constant function. Anytime you see a line that goes through the origin and it has a slope of 1, that means it's the y equals x function. That's called the identity function. And if you need to, you can actually plug this into your calculator and you'll see that it'll have the same exact characteristics every time. The most important thing is that it goes through the origin and that it has a slope of 1. Okay? Alright, the absolute value function, the most basic is y equals the absolute value of x. It's going to be the shape of a v. So anytime you see a function and it has the shape of a v, you automatically want to think, okay, it's the absolute value function. And then the quadratic function, it's a U-shape. It's a U-shape. Anytime you see that it looks like a U-shape, it's going to be a quadratic function. The absolute most basic one is y equals x squared. And particular characteristics, it goes through the origin. It goes through 1, 1, 2, 4, 3, 9, etc., etc. Looking at the absolute value function, we know it goes through 0, 0, and here on the right side it has a positive slope of 1, and on the left side it has a negative slope of 1. Okay? Moving on to our examples. It says, example 1, identify the function represented by the graph. Alright, so in this case you need to think, okay, what shape is this? Well, it's a V shape, and any V shape is going to be an absolute function graph. And that's your answer. Let's try one more. It says, identify the type of function represented by the graph. Well, in this case, we see that it's a U-shape, and we know that U-shapes are quadratics. So this belongs to the quadratic family. Now you're going to try two examples back to back. Example number 2, describe the translation in y equals x plus 1 squared, then graph the function. Here we actually are already given the function. First thing you want to do is remember the parent graph. Okay? So if you don't have the parent graph, you need to automatically graph it. So we know that this is a U-shape, and quadratics have an exponent of a 2. So if we graph the parent function here in blue, and then we graph our new function which was given to us, you can see, okay, I see that we moved to the left 1. Okay, so that's all you have to do, is you just describe what happened to your parent function, what happened, what did it do. And in this case, it moved 1 to the left. And what's interesting is that we can see what happened to our equation here. We have x plus 1. So I kind of think of the the parentheses when you have the x values. I think of this as kind of like backwards world. You would think that this would actually move it to the right because that's a positive 1, but in this case it doesn't. It moves it the exact opposite way we think it would. In this case it moved to the left 1. So that's just one thing to watch out for. Okay? If it's inside the parentheses with your x, it's going to move it to the opposite way. It's going to have a horizontal shift the opposite way you would think it would. Now it's your turn to try a problem. Example 3. Describe the reflection in y equals negative absolute value of x, then graph the function. Alright, so again, step number 1, you need to make sure that you graph the parent function. We know that the parent function to this equation is just going to be the regular y equals absolute value of x, which is graphed here in blue for us. When we plug the other one into our calculator, we actually get this green result. Now we're going to describe what happened. Well, we can tell that it actually flipped over the x-axis. Okay, so it flipped over the x-axis. And that's it. That's your answer. So, a couple things here. If it flips over some line, in this case, our x-axis was our line of reflection. Okay, now let's look at what we did to the equation. You see, if we have a minus sign being multiplied to our function, it means it's going to flip our function. That's interesting. Alright, you try one. Example 4. Describe the dilation on 1/2 absolute value of x, then graph the function. So again, what you want to do is actually graph your parent function first. Here we don't have our original graph. So you can plug it into your calculator and look at your table if you want. And I'm going to go ahead and graph our original graph, and you should have this memorized. So we know it goes through 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, negative 1, 1, negative 2, 2, negative 3, 3, negative 4, 4, and so on and so forth. So here's our original parent function graph. And when we multiplied the outside by 1/2, it looks like it had a vertical shrink. See how each of these y values kind of shrunk down? Okay, so we would say it had a vertical shrink of 1/2. Had a vertical shrink of 1/2. So anytime you multiply something on the outside of your function, it's actually either going to make it half as tall, or say if you multiplied it by a 3 times the absolute value of x, it's going to make it 3 times as tall. So that would be a vertical shrink or a vertical stretch. Alright, your turn. Number 5. The function f of x is negative 1/2 times x minus 5 squared plus 12.5. Can be used to represent a parabolic archway. Describe the transformations on the function, then graph the function. Alright, so on this, we have to think, okay, what is my parent function? We know the absolute basic is going to be y equals x squared, and you can tell because we have this little squared here. So we have to describe what happens to it. If you graph your function in your calculator, remember you go to the graph and you press tab if your function doesn't show up, and you can plug in your x squared, and then once you do that, press the tab button, and then you should be able to enter this into your calculator as well, so you should be able to see both. Alright, so what happens is this negative here is going to end up flipping my graph over the x. Okay, so that's the first thing that happens. Then we see that it's being multiplied by 1/2. Well, in our last example, we actually said, okay, that gave us a vertical shrink because it was less than 1. Now, that means my graph is going to be half as tall. So we have first, it flipped over the x-axis. 2, it had a vertical shrink of 1/2. Now let's look on the inside. Remember how I said earlier in the video, this is like backwards world. You would think if it says -5, you would think it would go 5 to the left. However, it doesn't. This actually means shifted 5 units to the right. And the last thing that happens is we have plus 12.5. And as you can see on your graph, that actually shifts my graph 12.5 units up. Now, make sure you actually graph this on your calculator because you might not understand where I got all this from. In a minute, you're going to be able to tell just from your equation how we get these transformations, but it's really, really important that you actually graphed it, okay? To end this video, this is our concept summary. All right, so we have our different transformations, meaning we're changing our basic parent function graph. And this is what happens to the parent graph. It's really important that you write every single piece of this down. Now, if you have something that's on the inside of your, on the inside with your x, you're either adding some sort of number or you're subtracting. Okay, if you add units inside, it actually translates your graph to the left. If you subtract them, it actually translates your graph to the right. Now, if your number is on the outside of the parentheses, it treats it just like you would think. If you're adding a number, it translates it up. If you subtract a number, it translates it down. Okay, now reflections. If you have your function being multiplied by a negative, it actually reflects the graph over the x-axis. But if it's on the inside with your x, it reflects it over the y-axis. And for your dilation, if you have a number being multiplied to your function and it happens to be greater than 1, so for instance like 3, it makes it 3 times as tall and it stretches your graph vertically. If the a value is like a fraction between 0 and 1, like 1/3 or 1/2, it compresses your graph vertically. It makes it half as tall, a third as tall, a fourth as tall, etc. If you have a number being multiplied inside your function value by your x, and it happens to be greater than 1, remember, I said when stuff is on the inside with your x, it's kind of like backwards world. You would think if that was a 3x that it would make it stretch, but it doesn't. It actually compresses your graph horizontally. And then if you have some number that's being multiplied, like 1/2, 1/4, 1/3, it actually stretches your graph horizontally. Okay? We'll go more in depth on this in 2.8. Just make sure you write this down and I'll be able to answer questions when I get back to school. Y'all have a great day. Also, if you're confused, please get the book and actually read the chapter. It really, really helps. I'll actually ask if you did it. I might give you 5 points if you did. Hint, hint.